It's another Dibs Physics video. What is up, fellow physics nerds? Mr. DeBello coming to you live clearly from your classroom. I snuck in here just to, check in on things, see how they're going. And what I want to do today is spend a little time in class just kind of going over the two homeworks that were due. So please make sure that you get these done if you have not already. And we're going to start with our position graph analysis homework. So let's jump into that one. All right. So for our lovely, bless you, little dude. Little kid is sitting right there, little poop machine. You guys want to see him? Here. Come here, buddy. Oh, there he is. He's a little poop machine. He eats, he poops, and then he looks around at stuff. That's pretty much it. So he's just chilling right here while we do this. All right, let's get you back. All right. Just chilling in the classroom with me, obviously. All right. So here was the graph that we had, and we were asked to first go through and describe the motion of an object at various points kind of along the journey of this thing. So if we take a look here, there were three things that we've talked about in class that we need to do when describing the motion of an object. First, what is the magnitude of the object's velocity? So if we can, we want to calculate the velocity of the object. So we're going to do that by finding the slope, right? And we could find slope using the same slope equation we've used in math for years. Rise over run, right? The direction of an object's velocity we could find by, again, looking at the slope of this type of graph, right? And whether or not it's positive or negative. And then is the object's velocity changing, we can look at, again, by looking at the slope and seeing if the steepness or the slope is actually changing over time. So let's look. First, we're asked, hey, what's the motion of the object from 1 to 2 seconds? So we're looking at this portion of time right here. So in that time, let's start by finding the slope. Oh, well, it's a flat line. So we can say very simply that the slope of the object, right, or that the object is not moving, right? We don't have to provide a direction, and obviously velocity is not changing there, right? So we would say not moving, and we must justify our answer. This is important. So when we have an assessment here, that justification part is going to be worth more points than obviously getting the answer. So you want to make sure that you could justify your answer, right? He's not moving, right? So I would say, since slope is 0, velocity is also 0. Okay, so now let's jump down here to our next one. Describe the motion of the object from 2 to 5 seconds. So from 2 to 5 seconds, let's take a look. Let's highlight that here in green. So from 2 to 5 seconds, this is what we're looking at. So now to describe the motion of the object, now the object's moving because there is a slope. So I can find that slope, right? I can do a little rise over run, just like we did on our last lab exercise. So when we do this rise over run, how much did we go up? We went from 10 to 20. So we went a positive 10 meters upwards, and then we went 1 second across. So if I was to find the slope of this, right, I could come over here and be like, all right, slope is delta y over delta x. So we had 10 meters in 1 second. So I would say the object was traveling at 10 meters per second, right? So we got the velocity of the object. Which way was it going? Well, again, let's look at the slope and whether or not the slope of this thing is positive or negative. We have a positive slope here. So which way are we going? Well, to answer this properly, we've got to go back to the original graph here. And it says this shows the position of a runner headed south. So what this is saying is south is the positive direction along our graph. So if we were to look at our graph and assume this is like a number line, that means that when we go this way along our number line, we are headed south, right? And if an object moves this way along the number line, we're headed north. So it's kind of backwards, right? But that's something we can do in physics. We can be backwards, it's fine, as long as we define it beforehand. So the object was traveling at 10 meters per second. Uh-oh, everything moved. Oh gosh, undo. Undo. There we go. The object was traveling at 10 meters per second south. Right? So the object's traveling at 10 meters per second south, right? And then we'll say also, was the slope changing? So that's the other question we've got to answer here. Was the slope changing? So if we look at this, is the slope changing? Well, here it's 10 meters per second. Do we have the same slope from here to here? And what about from here to here? Yeah, it's the same the entire time. Therefore, the slope is constant, which means our velocity is constant. So the object's traveling at 10 meters per second south at a constant velocity. Okay, so when we do this here, right, we now still need to justify our answer. So if you notice, we're always justifying our answer with the slope of the line. Because when we're asked to describe an object's motion, we're talking about the object's velocity. And since we're working with a position time graph, the slope of this graph is our velocity. So we can justify this entire thing with the slope. The object was traveling at 10 meters per second south at a constant velocity. This is because the slope of this line was positive and constant. Amazing. So let's go and look at 5 to 6 seconds now. So from 5 to 6 seconds, we're looking at this little interval in blue, right? Now, what do you guys think? Is the object moving faster, slower, or the same velocity as it was from 2 to 5 seconds? If you said, you all right, dude? I don't know if you guys can hear his hiccups right now. All right. So if you guys said faster, you would be right. And that's because the magnitude of the slope is greater. While it is negative, the amount is greater. So in half a second here, we're traveling down. We're going from 40 to 20, so we're going down 20 meters in just 0.5 seconds. So when we go to find the slope, we're going to be at a slope of 40 meters per second. So we would say the object is traveling 40 meters per second, right? And it's a negative slope, so it's traveling north, okay? And also at a constant velocity, right? So those are the things that I'm bringing in, that I'm answering the question with, and now I want to form that in a sentence. I would say, the object is traveling at 40 meters per second to the north at a constant velocity. This is because the slope of this line is 40 meters per second. The slope is negative, so the object is traveling north, right? Remember, this problem's a little backwards from what it normally is, right? And the slope is constant, right? So the object's traveling at a constant velocity. Again, if I do the same slope over here, it's the same, right? So that slope is not changing. All right. And now lastly here, how many times does an object change directions in this situation? Well, what we need to think about is how we know whether or not an object changes direction, right? We know that when the slope is positive and negative, when that slope changes signs, when our velocity changes from positive to negative. So how many times does it go from positive to negative? So if we look at it here, let's look at all the points where the slope just changes. Here it goes from positive to 0. That doesn't really change the direction. Then here it goes from 0 to positive again. So we're still moving in the positive direction, which in this case is south. Then finally here, oops, I don't know how I did that. Here at this point, right, what are we looking at? Oh, here's a change. We go from positive to negative slope. So there is only one time where the object changes direction. So I would say one time at, and we could say the point at which it changes direction. We know it changes direction at exactly 5 seconds into its journey, right? So at 5 seconds. So, and we know this, we would justify our answer by saying because the slope changes from positive to negative. All right, and we'll be right back and we'll go over the story portion of this. All right, so for this section, we had to come up with a story for this graph. So I'm just going to kind of highlight each section individually, and then we'll just kind of talk about what's going on there. And I'm going to come up with my own story, and you can compare and kind of see how you did. And I'll talk about kind of what I was looking for here. Like a big thing was, you know, was the object increasing or decreasing its velocity? Right? What direction was the object going? All of the things that we talked about previously had to be part of your story. So first thing I'm going to do is kind of look at, you know, like the actual amounts, right? So in this first leg, this is an object that's traveling 60 meters in 10 seconds. So is that really good for a car that's driving? Not really. A car's going to drive a lot more than 60 meters in 10 seconds. So maybe it's better as a person running. So maybe I'll do this as kind of like a football field, right? Because I'm looking and I'm going, okay, we got like 60, 40, right? Hey, you know, we could be doing a little football field action maybe, right? So let's go. Let's start this off and say, all right, first, this is, you know, maybe towards the end zone, right? Towards end zone, right? This is going to be the halfway mark of the field, so the 50, which is kind of, I'm going to put that in quotes because it's not the 50-meter mark, it's, you know, 50, line being the center, and then going back, right, 40 meters, we have what happens. So let's kind of go through this. So for this first leg, right, let's say a wide receiver starts running a play, and they run 60 meters forward from the halfway line. So they start at the halfway line, and they run 60 meters towards the end zone in 10 seconds at a constant speed. And I know that it's constant because the slope is not changing here. So they then stop in the end zone for 5 seconds, right? And we'll say they stop in the end zone for 5 seconds in disbelief because the quarterback ran all the way back towards his defensive end zone. I don't know football, man, and got sacked. So he's got to jog all the way back to where his quarterback was sacked, right? 40 meters behind the halfway line on the field, right? But as soon as he does, there was a flag on the play, and a timeout was called. So he has to jog again back to the halfway line and get off the field for a timeout. So that's my story. That's kind of how I would lay it out. Each of the cases, I want to say that his speed was constant, and I want to make sure that I'm indicating direction. So that's kind of a sort of realistic story for the scale of the numbers here. So hopefully you guys had something like that. So now before we jump into your most recent homework, the direction of acceleration homework, let's go to your notes. So let's hop into page 18 of your notes packets right now and talk about constant speed and accelerated motion. So in each class, we did some stuff with the motion sensors, right? And we noticed that when an object is traveling at a constant speed, we always get a straight line, right? So we get that straight line when we're traveling at a constant speed. So this would be a constant speed going forward. Maybe we also could have a constant speed going backwards, right? So constant speed is always constituted by a straight line. However, accelerated motion is when an object is changing its velocity as time goes by. So we noticed when I went outside on my rollerblades, right, we got a graph that looked like this. A curving graph showing me increasing my speed as time went on. As you can see here, the slope of this graph is getting steeper and steeper and steeper as time goes on. However, it doesn't always have to look like this. A graph that looks like this, oops, I wanted to change colors there. Let me go back and do that, right? A graph that looks like this is also an example of acceleration, but in this case, the object is slowing down, right? And you could also have something like this. This is also an example of acceleration. Anytime that line curves, an object is accelerating and changing its velocity. So let's talk about how to calculate acceleration. In your reference tables, we have an equation for acceleration, which is very similar to our equation for finding velocity. So acceleration is a change in velocity over time. Uh-oh, little dude's upset. Let's be right back. And we're back. So in this problem, we have Chaz sitting down on a skateboard, and the speed of that skateboard increases in a period of time. So what we want to do is first kind of list out what we know, okay? So anytime we're solving a problem, especially with these problems, what I like to do is list out initial velocity, final velocity, acceleration, and time, right? And I like to just put like a bar like this, just to kind of make a nice, neat chart. And then what I like to do is first put a question mark next to what we're looking for in the problem. So it asks, what is the magnitude of acceleration? So acceleration is a vector quantity. It has a direction. You're going to see this word a lot, and I don't want it to confuse you, because a lot of people are like, what's magnitude? How do I find magnitude? You're not finding magnitude. You're finding the magnitude of the acceleration. So you're just finding acceleration in this problem, okay? And what that says, when you see what is the magnitude of the acceleration, it means I just want the amount, not the direction. So it actually makes the problem a little bit simpler. We don't have to worry about north, south, east, west, up, down, forward, backwards, any of that stuff. So let's go and write in everything else that we know. So we know the initial velocity of Chaz was 2.5 meters per second. Then he starts going down the hill, as Chaz would do, and ends up with a final velocity of 9 meters per second. And he does all of this in a time of 3 seconds. So now let's use our equation, which we already wrote down, A equals delta V over T, and let's substitute into that equation. So let's go A equals. Now the delta V part of this is kind of tricky. Do we do 2.5 minus 9 or 9 minus 2.5? As we talked about kind of at the start of the year when talking about displacement, we always use the same order. It's always final minus initial. So we could rewrite our equation like this. This is something you might want to add to your reference table if you feel like you're not going to remember this. Now I can go and substitute the values. I'm going to do 9 meters per second minus 3 meters per second, all over a time of 3 seconds. So what do we get here? We get 9 minus 3, which is 6 divided by 3. I think I can do that one in my head, and hopefully you can too. That is going to be 2. And the units, meters per second per second. So we have 2 meters per second per second. We're often going to write that a slightly different way. You'll often see us write that as A equals 2 meters per second squared. So those mean the exact same thing. So this means Chaz was increasing his velocity by 2 meters per second every second. So let's look at some of the other problems that we have here. Mr. DeBella was driving his beat-up Honda Civic in Maine when a moose steps onto the road in front of him. This actually happened to me. I was going skiing in Maine. We were there in the morning. And I don't know if anyone has seen a moose before, but my God, I saw it, and it was early in the morning. I was drinking my coffee, and I thought I saw a dinosaur because I was not entirely awake yet. It scared the crap out of me. A moose is huge. I don't think people understand the size of moose when we just see them like on TV, unless like you live there. So me and my friend, we saw a moose and we freaked out and just slammed on the brakes. So we went from 30 meters per second to rest in 0.35 seconds. What is the acceleration of the car as Mr. DeVello skillfully avoids hitting the moose? So now in this one, notice we don't see that word magnitude as we did in the past one. So in this one, we are going to have to take into account direction. Let's see how the equation is going to do that for us. Okay? So let's define our positive and negative directions here just to make sense. Positive is going to be forward, right? That's easy. And we'll say backwards is negative. So just for this problem, we can always kind of think about this. For every single problem, every single one can be different. You can set it up however you would like. So now let's go and list what we know. So I'm going to start again with the same stuff, VI, VF, A, and T. Now, this time again, we're being asked for acceleration, so I'll put my question mark there. I always like to put that question mark in terms of what we're finding in there first. It kind of helps, I think, mentally when you're doing this problem, it helps focus the problem a bit more. All right, so now let's go in and grab the other values that we have. So Mr. Bell goes from 30 to rest, 30 meters per second to rest. So my initial velocity is 30 meters per second, and that's going to be positive because we are moving forward, right? Then my final velocity is at rest. That's a word we're going to see a lot in physics this year. And at rest means we are at 0 meters per second. Okay? And all of this happens in 3.5 seconds. So now we have all of this lovely information. So what do? All right, well, we've got to use our equation that we've had before. A equals, and I'm just going to write it out like this from the start, VF minus VI over T. So now I've got to substitute into that equation here and get our answer. And you'll notice if you're kind of thinking ahead right now, something interesting is going to happen. We're going to end up with 0 minus 30 all over 3.5 seconds. So we're going to end up with a negative number here. So what I'm going to do, I'm going to bring up the calculator. See if we can get this to work. There we go. So let's turn it on. There we go. All right, awesome. So we're going to do negative 30 divided by 3.5. So at least this way you guys can see my calculator input, what I'm typing in on the screen here. So I'm also going to show you guys how I'm going to round. So I'm going to take here, let's see if this works. Okay, I'm going to take the first 3 digits of this number. So I want that 8.57. But before I write that down, I'm going to look at the next digit, that 1. That 1 does not round the 7 up. So I'm going to take that negative 8.57. So we go negative 8.57. And now I've got to put my units in, which is going to be meters per second, or meters per second squared. So there's our answer, sort of. We've still got to handle this negative sign because we don't want to give negative. What does a negative mean? We want that context. So this means the direction of my acceleration was backwards, right? Because we identified backwards as our negative direction. So this is going to be 8.57 meters per second backwards. So I'm going to get rid of the negative sign and add the real direction in there. Okay, so my head's kind of blocking this now. Not ideal. All right, so what I think is kind of interesting about this is, how is my acceleration backwards if this entire time my car was only going forwards? So this is going to bring us to the other homework that we had to do, which was acceleration direction. So we talked about this in class, we took notes on it, and we said if acceleration is in the same direction as our velocity, we will increase our speed. But if our acceleration is opposite of our velocity, we'll decrease our speed. So the best way to think about the direction of acceleration is not to think about the direction an object's going. That's going to be the direction of the object's velocity. Instead, think about the direction the object is being pushed. That's what acceleration is going to be. So let's look at a few of these examples here. Okay? So in this example from your homework, we have a truck that's going north, right? So that means north is positive and south is negative, right? Now, if the truck is traveling north, so our truck is actually traveling north, if you wanted to slow this truck down, which way would you have to push? Well, you would have to push that way to slow it down. So the direction of our acceleration would be south. So the answer here is south. Okay. This next one, Zanab goes bungee jumping. As she's falling downward, bungee cables start to slow him down. What is the direction of Zanab, or should be slow her down? Sorry, these are all students from last year. I didn't change it. Sorry. What is the direction of Zanab's acceleration? So this one's kind of weird, right? We've got, instead of north and south this time, we've got, let me try to use the same colors. Sorry, guys. We've got up and down. So we've got up and down. So we'll use another blue arrow to represent Zanab's velocity. So she's falling downward, right? So Zanab is going downwards. But that bungee cable is pulling on her which way in order to slow her down? That bungee cable is going to pull on her this way. So her acceleration, let's label these just to make sure everything's clear. Her acceleration is going to have to be upwards. Okay. Next one. Cruz is an elite curling star and is competing at the Olympics. He pushes off to the south and speeds up while holding the rock. While he was speeding up, what was the direction of his acceleration? Okay, so let's say here's a person. Let's get a little stick figure action going, right? A little curler. Yeah, it's a top tier drawing. All right, so this person pushes off. So we're going to say this is forward, and this is backwards. It's kind of funny, like writing this, like it seems so obvious, right? But you know, it's kind of hard to communicate some of these things, so we have to make sure we're being very specific with our language. So let's say forward is positive, backwards is negative. That's going to help us when we're doing math. And in this problem, we're not doing math. We just need that direction. So if his velocity is directed this way, so he's increasing his velocity this way, he's pushing his body this way. So he's accelerating in the same direction as his velocity. So his acceleration is also going to be forward. Okay? Let's go on to I think the last one here. Frida gets a shiny new sports car. She decides it would be fun to accelerate as quickly as possible. She gets her car pointed north. So we're going to have north and south as kind of our directions here. We could give some positives and negatives, right? So Frida stops accelerating at 60 miles per hour. What is the magnitude direction of Frida's acceleration if she does this in 4.8 seconds? So Frida is moving north. She's driving north the entire time, but she's speeding up. So that means she's being pushed forward towards the north as well. So we know our acceleration is going to be forward. So we're also asked for the magnitude and direction of Frida's acceleration. So let's calculate it. A equals final velocity minus initial velocity over time. So we're going to go through that same process we were going through in the problem before here. So in in this case, Frida's final velocity is 60 miles per hour, and we know that Frida starts from rest. And she does all of this in 4.8 seconds. Okay, so now all we've got to do here is plug this into our calculator. So let's bring up our calculator again here. Turn it back on. And now we're going to have 60 divided by 4.8. And we're looking at 12.5. And this is going to be meters, or not meters per second squared, but miles per hour per second. So we've got miles per hour per second. And we've also got to make sure that we include the direction as well. And we've already talked about that here. The direction is going to be north. So there we go. All right, so hopefully this kind of helps understand a little bit more about what acceleration is. All right, so what we'll do is we'll kind of end this video here, just kind of going over stuff. The next video, we're going to go into a few more topics regarding acceleration and how it ties into some motion graphs. All right, see you guys in the next one.